Good morning, everyone. My name is Khushi from BSc Chemistry Honors, second year, and today our chapter is Infrared Absorption Spectroscopy. Infrared absorption spectroscopy concerns the absorption of radiation in the infrared range and is probably the single most widely used method for investigating the structures of organic substance. The instrument used for recording the infrared spectra is known as infrared spectrophotometer. The infrared region of electromagnetic spectrum ranges from 0.8 to 200 micrometer. Basic theory of spectroscopy: molecular vibration. The atoms constituting a molecule are not held rigidly in a fixed position. They are continuously rotating and vibrating in a number of ways. To have an idea of molecular vibrations, let us compare a bond between two atoms in a molecule to a weightless spring connecting two balls together. Just as the spring can be compressed, stretched, or bent, the bonds can be stretched or bent, giving rise to the vibration in the molecule. There are two main kinds of molecular vibration. These are stretching vibration and bending vibration. First, stretching vibration or bond stretching. In a simple diatomic molecule AB, the only vibration which can occur in rhythmic compression or extension along the AB bond. This type of periodic back and forth movement of the atoms along the covalent bond axis, which can be compared to that of a coiled spring, is known as stretching vibration or bond stretching. Types of stretching vibrations. In triatomic or higher molecules, the stretching vibration can be of two types. First, symmetric stretching. It is the stretching vibration in which the movement of atoms with respect to a central atom in the molecule is in the same direction. In other words, all the bonds toward the central atom are either stretched or compressed simultaneously. Second, asymmetric stretching. The stretching vibration in which one atom moves towards the central atom while the other moves away from it. In other words, one bond is stretched and the other bond is compressed. Bending vibrations or deformations. In triatomic and higher molecules, there can be another type of vibrations involving changes of bond angles. Such vibrational moments are referred to as bending vibration or deformations. Bending vibrations may be defined as the periodic changes in bond angles between bonds formed by two atoms with the central atom. Types of bending vibration. Bending vibration can be of four types. Scissoring. This is an in-plane bending vibration in which the two atoms move towards each other. Rocking. This is an in-plane bending vibration in which the two atoms moves in the same direction. Wagging. This is an out-of-plane bending vibration in which the two atoms move simultaneously either above or below the plane of system with respect to the central atom. Twisting. This is an out-of-plane bending vibration in which one atom moves above the plane, other moves down the plane. Scissoring and rocking present in plane bending, while wagging and twisting represent out-of-plane bending. Principle of IR spectroscopy. We know that atoms constituting a molecule are not held rigidly in fixed position. They are continuously rotating and vibrating in a number of ways. The various modes of vibration possible in a molecule depend primarily on the nature of bonds themselves and to an extent nature of entire molecule. Absorption of infrared radiation by a bond increases the amplitude of vibration and also brings changes in rotational energy level. However, in the infrared range usually studied, the absorbed energy bring about predominant changes in the vibrational energy levels. It is obvious that a given bond or a part of molecule can absorb only the wavelength of infrared radiation, which will provide the photon of that particular amount of energy which is required to raise the vibration energy level to a permitted value. The record of the amount of infrared radiation of different wavelengths absorbed to the raise the vibration energy level constitute the infrared spectrum of molecule. Units in IR spectrum. The position of absorption infrared radiation in IR spectroscopy is generally expressed in the terms of wavelength in micrometer, micron, or in terms of wave number, which is in centimeter inverse. However, wave number is usually treated as absorption band frequency. The wave number corresponding to the wavelength of infrared radiation range usually studied. Calculation of vibration frequency. Hooke's law. The molecules of organic compounds usually contain C and CH bonds and also some other bonds. Therefore, the analysis of various modes of vibration for a molecule is very difficult because all the atoms present in the molecule contribute to the vibrational modes. However, it is still possible to calculate approximately where a particular vibration mode will appear in the infrared spectrum by considering each bond present in the molecule once at a time and ignoring the other. Here the K is force constant, which is in 9 centimeter inverse, which is related to the strength of the bond. Mu reduced mass in grams per atom. It is calculated as mu is equals to m1 m2 divided by m1 plus m2. Hooke's law: if a body of mass m, factors which determine the vibrational frequency. The simple analogy between two bonded atoms and a simple oscillator help us in knowing the frequency of various absorption bands in the infrared spectrum from the nature of atoms and strength of bonds between them as illustrated. The smaller the mass of bonded atom, the smaller the reduced mass and therefore higher its vibrational frequency. In other words, vibrational frequency is inversely proportional to reduced mass. The bonds between hydrogen and other atoms have the highest non-fundamental frequencies, but covalent compounds of halogens and most metals show infrared absorption to a lower frequency, which are low to be recorded on return or on routine spectrophotometer. That is all about it. Example: number of fundamental vibration. It has been stated earlier that absorption of infrared radiation have energy equal to the difference between two vibration energy levels will lead to a vibrational transition. In the transition from ground state to the first excited state, light absorbed is strongly as a result of intense bands called fundamental absorption band, which are produced. The number of fundamental absorption bands is equals to number of fundamental vibrational modes. Since a diatomic molecule has only one fundamental vibration mode, that is stretching vibration, it gives rise to one fundamental absorption band. However, polar atomic molecules can have more than one kind of vibrational moment. They exhibit more than one fundamental absorption band as given below. Non-linear polar atomic molecules. It has been found that non-linear polar atomic molecules can have 3 and minus 6 modes of fundamental vibration. Linear polar atomic molecules or linear polar atomic molecules have n atoms, which can be 3 and minus 5 fundamental vibration. Some of fundamental vibration may be very weak and therefore may not be recorded as band. Some of the fundamental vibration may be very close and result overlapping of band. Some of the fundamental vibration involve energy changes which fall outside usual IR range. Selection rule: most of the molecules possess dipole moment due to the presence of polar bonds linking the constituent atoms. When the polar bond undergoes stretching vibration along the internuclear axis, a change in electron distribution of bond takes place. As a result, dipole moment also undergo change. In other words, a vibration produces a fluctuating dipole moment. Interaction between the oscillating dipole moment and the infrared radiation leads to the absorption of energy from radiation, so that energy of vibration increases. Position and intensity of bands. Position of absorption band. Depending upon the types of bond present in a molecule, various wavelengths are found to be absorbed in the infrared spectrum of the molecule, giving rise to absorption bands. The position of absorption band depends upon the nature of bond or group. Absorption band characteristics of a particular bond or group indicates the presence of that bond or group in the molecule. For instance, in the spectrum recorded, the absorption band at 3 micrometer clearly established the presence of hydroxyl group in the molecule. Similarly, the absence of characteristics absorption band of a bond or group guarantees the absence of that particular bond or group. It may be noted, however, the actual absorption pattern of the bond or group may vary slightly from one type of molecule to the other. Infrared spectrum can be visually divided into two regions: functional group region and the second one is fingerprint region. Functional group region. In general, absorption bands from 2.5 to 8 micrometer are associated with the changes in vibrational states of various bonds. According to this region, is characteristics of the types of bond present may be termed as functional group region. Fingerprint region. Absorption bands in the region rotational changes of a molecule as a whole is known as fingerprint region. Intensity of absorption band. Different absorption band in the infrared spectrum have different intensities. The intensity of absorption band is mainly dependent on the molecule of change of dipole moment. The more the polar character of a bond, the greater the change in dipole moment and the greater the intensity of absorption. For example, a carbonyl group has a much higher dipole moment than double bond, and therefore it give rise to stretching absorption bands of much higher intensity than C double bond stretching bands. Factors influencing vibration frequency. We have seen that probable frequency of a bond in an IR spectrum can be calculated with the help of Fock's law. However, it has been found that the calculated value for a bond is only in the tolerable agreement with the experimental value but never equal to it. This is because the vibration of each group is influenced by the structure of the rest of molecule in its immediate neighborhood. The important factor responsible for the vibrational shift are electronic effect. When the substituent in the neighborhood of a particular group are changed, it brings about changes in the absorption frequencies of that group due to electronic effects such as inductive effect and resonance effect. Inductive effect: the presence of alkyl group is the vicinity of a particular group causes plus effect. As a result, the bond length of that group tends to increase or the bond strength decreases. Consequently, the force constant is lower and frequency or wave number of absorption decreases. Third, resonance effect. Resonance effect has significant influence on the absorption frequencies in the infrared spectra of many compounds. For instance, conjugation lowers the absorption frequency or wave number of ethylenic bond in conjugated dienes and the carbonyl group in conjugation with ethylenic bond or aromatic rings. Second, hydrogen bonding. The infrared spectra of organic compounds such as alcohols, phenols, carboxylic acid, and amines which exhibit hydrogen bonding are strongly influenced by the presence of hydrogen bonds. Hydrogen bonds resulting in the weakening of the bonds involved so that the force constant decreases and absorption shift towards lower frequency or wave number. Some important generalization about the role of hydrogen bonding in the infrared spectroscopy are: first, the stronger the hydrogen bonding, the greater the downward shift in the absorption frequency. Second, intermolecular hydrogen bonding give rise to broader bands, while intramolecular hydrogen bonding give rise to sharp and well-defined bands. The intensity of absorption bands in the intermolecular hydrogen bonding is concentration dependent and decrease with dilution. In contrast, concentration has no effect on the intensity in case of intramolecular hydrogen bonding because it takes place within the same molecule. The downward shift is more pronounced in case of intermolecular hydrogen bonding than intramolecular hydrogen bonding. Let us illustrate about generalizations with some example. Alcohols and phenols. Alcohols and phenols. In case of both alcohols and phenol, the free OH group give rise to to strong absorption bands in the region 3650 to 3600. On the other hand, the hydrogen bonded OH group give rise to absorption band in the region 3400 to 3200 centimeter inverse. Carboxylic acid. Carboxylic acid generally exists as dimers having strong intermolecular hydrogen bonds. Due to large strengths of hydrogen bonds, there is a large decrease in absorption frequency of C double bond O and OH stretching vibration frequencies in these dimers. Thus, carboxylic acid dimers exhibit a very broad band due to the OH stretching at 3000 से 2500 centimeter inverse for the free OH group. Similarly, there is a downward shift for C double bond or stretching in acid from about 1750 centimeter inverse to about 1700 centimeter inverse. Amines. Due to relatively weaker bond in amines, the downward shift in the absorption frequency of NH bond is only for about 3500 centimeter inverse to about 3300 centimeter inverse. This is much lesser than in case of OH bond in alcohols and carboxylic acid. Vibrational coupling. It has been observed that in some groups containing two or more similar atoms to a central atom, the bond is different from that of the isolated bond. This is due to mechanical interaction between the stretching vibration of the bonds known as vibrational coupling. Instrument mechanics of recording their spectra. The first, sources of infrared radiation. A common source for infrared radiation is the nernst glare, which consists of a mixture of zirconium oxide, yttrium oxide, erbium oxide heated electrically to about 1775 Kelvin. Infrared radiation can also be produced by heating a rod of silver carbide globe electrically. The beam of infrared radiation is split into two beams. One beam passes through the sample cell while the other passes through the reference cell, which contains only the solvent. The two beams are alternatively allowed to enter the monochromator by means of a rotating Mirror. Sample containers. The sample under examination may be employed in the gaseous, liquid, or solid or solution form. However, solids scatter the radiation too much if placed in the path of light. As such, they are either dissolved in organic solvents such as CCl4, CHCl3, CS2, or ground with nuzole, liquid paraffin to form a mull, or converted into a pellet with potassium bromide. The sample containers, cold cells, and the optical parts of the spectrometer are made of rock salt, which is rock salt is NaCl, and certain other alkali metal halides such as CSI, since glass is opaque to infrared radiations. Monochromator. By means of prism or diffraction gratings, the monochromator allows radiation of only one frequency to enter the detector at a time. The frequency of radiation get automatically varied detector. The detector scans the range of infrared radiation frequency received from the monochromator and transforms the energy of radiation received into electrical signal. This signal is proportional to the difference in the intensity of radiation in this sample reference beam. Fifth recorder. The detector signal is sorry is automatically recorded on a chart paper showing intensity of transmission as a function of wavelength and frequency of infrared radiation. In the actual practice, it is transmitted light from 0 to 100%, which is plotted in infrared spectra. For recording the infrared spectrum, a very small amount of sample is needed, but the sample used must be absolutely dry, but water gives strong absorption near 2.7 micrometer. More sophisticated and sensitive spectrometers are now available and gradually replacing the instrument used earlier. One such spectrometer is Fourier transform infrared FTIR infrared spectrometer, which has a much better sensitivity and takes only 1 to 2 seconds for recording the spectrum. The infrared spectrum of ethanol CH3CH2OH is shown in the figure. Down the figure, it depicts clearly the absorption band which results from the stretching bands and binding vibration of carbon hydrogen and oxygen hydrogen and carbon oxygen bonds. Characteristics absorption regions of various bonds. The characteristics infrared absorption of different regions of various types of bond and functional groups are collected in the form of tables called correlation table. The correlation of the data on absorption of pattern of some important bonds and functional group. The letter S, M, omega, V denote the intensity is strong, moderate, weak, or variable. It is remembered that however the table gives approximate position of absorption bands, but already stated the exact position of absorption band of a particular bond depends upon the actual molecular environment. Spectral feature of some classes of compounds. Having discussed the fundamental aspects of infrared spectrometer in the previous section, we now take up the spectral features. Some classes of compounds. Hydrocarbons. The alkanes. Infrared spectra of alkanes are generally quite simple and not informative because alkanes do not contain any functional group. The most common peaks are absorbed. A bond is different from that of the isolated bond. This is due to mechanical interaction between the stretching vibration of the bonds known as vibrational coupling. Instrument mechanics of recording their spectra. The first, sources of infrared radiation. A common source for infrared radiation is the nernst glare, which consists of a mixture of zirconium oxide, yttrium oxide, erbium oxide heated electrically to about 1775 Kelvin. Infrared radiation can also be produced by heating a rod of silver carbide glober electrically. The beam of infrared radiation is split into two beams. One beam passes through the sample cell while the other passes through the reference cell, which contains only the solvent. The two beams are alternatively allowed to enter the monochromator by means of a rotating mirror. Sample containers. The sample under examination may be employed in the gaseous, liquid, or solid or solution form. However, solids scatter the radiation too much if placed in the path of light. As such, they are either dissolved in organic solvents such as CCl4, CHCl3, CS2, or ground with nuzole, liquid paraffin to form a mull, or converted into a pellet with potassium bromide. The sample containers, cold cells, and the optical parts of the spectrometer are made of rock salt, which is rock salt is NaCl, and certain other alkali metal halides such as CSI, since glass is opaque to infrared radiations. Monochromator. By means of prism or diffraction gratings, the monochromator allows radiation of only one frequency to enter the detector at a time. The frequency of radiation get automatically varied detector. The detector scans the range of infrared radiation frequency received from the monochromator and transforms the energy of radiation received into electrical signal. This signal is proportional to the difference in the intensity of radiation in this sample reference beam. Fifth recorder. The detector signal is sorry, is automatically recorded on a chart paper showing intensity of transmission as a function of wavelength and frequency of infrared radiation. In the actual practice, it is transmitted light from 0 to 100%, which is plotted in infrared spectra. For recording the infrared spectrum, a very small amount of sample is needed, but the sample used must be absolutely dry, but water gives strong absorption near 2.7 micrometer. More sophisticated and sensitive spectrometers are now available and gradually replacing the instrument used earlier. One such spectrometer is Fourier transform infrared FTIR infrared spectrometer, which has a much better sensitivity and takes only 1 to 2 seconds for recording the spectrum. The infrared spectrum of ethanol CH3CH2OH is shown in the figure. Down the figure, it depicts clearly the absorption band which results from the stretching bands and binding vibration of carbon hydrogen and oxygen hydrogen and carbon oxygen bonds. Characteristics absorption regions of various bonds. The characteristics infrared absorption of different regions of various types of bond and functional groups are collected in the form of tables called correlation table. The correlation of the data on absorption of pattern of some important bonds and functional group. The letter S, M, omega, V denote the intensity is strong, moderate, weak, or variable. It is remembered that however the table gives approximate position of absorption bands, but already stated the exact position of absorption band of a particular bond depends upon the actual molecular environment. Spectral feature of some classes of compounds. Having discussed the fundamental aspects of infrared spectrometer in the previous section, we now take up the spectral features. Some classes of compounds. Hydrocarbons. The alkanes. Infrared spectra of alkanes are generally quite simple and not informative because alkanes do not contain any functional group. The most common peaks are absorbed. Alkanes. Infrared spectra of alkanes are generally quite simple and not very informative because alkanes do not contain any functional group. The most common peaks exhibited by alkanes are given below: CH3, CH2, CH3, CH stretching absorption region in the region of 2960 to 2850 centimeter inverse. Alkenes. Infrared spectra of alkenes show many characteristics absorptions which can be very useful in the structure determination. The most prominent peak is the vinylic double bond CH stretching at a slighter greater than 3000 centimeter inverse. The actual position depending upon the extent of substitution in the alkene. C double bond C stretching vibration give rise to bands of variable intensity at 1620 centimeter inverse. Conjugation shift the position to lower frequency and increase the intensity of absorption. Alkynes. They exhibit strong absorption bands for triple bond CH stretching near 3300 centimeter inverse and other intense bond triple bond CH band at 650 to 611 centimeter inverse. Cycloalkanes mainly exhibit CH stretching absorption bands. The region of absorption moves to higher values with the increase in angle strain. For example, CH stretching for cyclopropane is 3050 centimeter inverse, while that of cyclohexane is 2990 centimeter inverse. Aromatic hydrocarbon. These compound exhibit CH stretching absorption at 3050 centimeter to 3000 centimeter inverse. And following hydroxy compounds. Alcohols. The OH functional group of alcohols give a characteristics OH stretching absorption band in the infrared spectra, but as we might expect, this absorption is significantly influenced by hydrogen bonding. If there is no hydrogen bonding, which is possible if dilute solution of alcohol is non-polar, it is used, and alcohols gives a sharp variable band at 3640 to 3610. In the associated state involving intermolecular hydrogen bonding, a strong broad band appears at 3400 से 3200 centimeter inverse. In case of intermolecular hydrogen bonding, the OH stretching band appears at 3700 से 3400 centimeter inverse and is of variable intensity. In addition, alcohols exhibit a strong and broad band in the range of 1200 से 1000 centimeter inverse due to CO stretching. The exact location of the band depends upon whether the alcohol is primary, secondary, or tertiary. Therefore, it can be used to determine the class of alcohols. Second, phenols. As in case of alcohols, phenol exhibit a strong band due to OH stretching in the range 3600 से 3200 centimeter inverse. However, the CO stretching band in phenols appears at in the higher region about 1230 centimeter inverse as compared with alcohols 1200 से 1000 centimeter inverse. Ethers. The infrared spectra of ethers are characterized by strong absorption bands in the region 1300 to 1000 centimeter inverse due to CH stretching vibration. Alkyl ethers show a single absorption in the range of 1150 से 1060 centimeter inverse. Aryl and vinyl ethers exhibit a strong band in the region of 1275 से 1200 centimeter inverse and a weaker band in the region of 1200 से 1035 centimeter inverse. Aldehyde ketones. The infrared spectra of aldehyde ketones are extremely useful in detecting the presence of these compounds. The carbonyl group in these classes of compounds show a C double bond or stretching band around 1700 centimeter inverse. The actual position of band depending upon the nature of groups attached to the carbonyl group. Aldehydes. The position of C double bond or stretching absorption band in aldehydes varies slightly according to the aldehyde, saturated aliphatic aldehyde or aromatic aldehyde, alpha beta unsaturated aldehyde. Further, the presence of electron releasing group plus I should the lower value, while the electron attracting group like minus I to higher attractive value. Ketones. The C double bond or stretching band in ketones appears at lower frequency or wave number as compared to aldehydes due to large plus I effect operating in ketones. The C double bond or stretching absorption takes place at a still lower value, alpha beta unsaturated. Carboxylic acid. The infrared absorption spectra of carboxylic acid exhibit a number of absorption bands which are helpful in the detection of C double bond OH functional group. There is a very broad and intense band in 3000 से 2500 centimeter range due to OH stretching. This is clearly indicative of stronger hydrogen bonding than in alcohols, where the OH stretching band is in the region of 3600 से 3200 centimeter inverse. Another strong band appears around 1700 centimeter inverse due to C double bond or stretching. In addition, carboxylic acid also show a CO stretching band at about 1250 centimeter inverse and a banding band for about OH near 1400 centimeter inverse and 920 centimeter inverse. Carboxylic acid derivatives. As expected, the infrared spectra of acid derivatives are characterized by the presence of strong C double bond or stretching bands. The exact frequency of the band depending upon the nature of compound. Thus, acid chloride shows strong band at 1815 से 1785 centimeter, while acid anhydrides exhibit two strong bands at 1840 से 1800 centimeter inverse and 1780 से 1740 centimeter inverse. However, in conjugated acid chlorides anhydrides. These bands occur at 15 से 20 centimeter inverse lower frequency. Amide shows the double bond or stretching bands at 1690 से 1650 centimeter inverse. Saturated aliphatic esters gives the C double bond O band around 1740 centimeter inverse. Alpha beta unsaturated esters and aryl esters exhibit this band at 1730 से 1715 centimeter inverse, while vinylic and phenyl esters show the band around 1770 centimeter inverse. This is the way to distinguish between them. Amines. The infrared spectra of amines show characteristics absorption band due to NH stretching, NH bending, CN stretching. The number and position of band depends upon the class to which the amines belongs. Primary and secondary amines exhibit moderately weak absorption band at 3500 से 3200 centimeter inverse due to NH stretching vibration. However, primary amines have two such bands in the region, while secondary amines show only one band. Tertiary amines don't have any NH band in the molecule and therefore they don't exhibit such band. Hydrogen bonding tends to shift the NH band to lower frequencies, but the shift is not as much as in case of hydroxy compounds. This is because the hydrogen bonding in amines is weaker than that in hydroxy compounds. Primary amines exhibit moderately strong NH bending. At 1650 से 1560 centimeter inverse and 900 से 650 centimeter inverse, while secondary amines show weak bands of this type around 1600 से 1500 सेंटीमीटर इनवर्स. The CN stretching bands of aliphatic amines appear in the region of 1230 से 1030 सेंटीमीटर इनवर्स. Tertiary amines generally show two bands. The intensity of absorption being weak. On the other hand, aromatic amines exhibit two strong bands at 1360 से 1180 सेंटीमीटर due to CN stretching. These bands may be used to distinguish between aliphatic and aromatic amines. Nitriles. The infrared spectra of nitriles are characterized by the presence of C triple bond stretching absorption band at 2260 से 2200 सेंटीमीटर inverse variable conjugation with double bond or aromatic ring shifts the absorption to lower frequency nitro compounds. The infrared spectra of nitro compounds show two strong bands at about 1560 से 1350 सेंटीमीटर inverse due to symmetrical and asymmetrical stretching of and double bond O bonds. Primary nitro compounds show two bands at 1560 से 1350 सेंटीमीटर inverse due to symmetrical and asymmetrical stretching of and double bond O bonds. Primary nitro compounds absorb at higher frequency as compared to secondary, while tertiary compounds absorb at even lower frequency. Conjugation of nitro group with an aromatic ring moves these bands to lower frequency. For example, nitrobenzene show absorption bands at 1525 से 1350 सेंटीमीटर inverse. Interpretation of IR spectra. Having studied the characteristics absorption position of various functional groups, we give below very useful tips for remembering the specific absorption regions and interpreting the infrared spectra. Remembering the specific absorption regions. For the purpose, the infrared range from 4 to 700 centimeter inverse may be broadly treated as consisting of four parts. The region from 4,000 to 2500 centimeter inverse is the absorption region of CH, OH, NH single bond stretching. The region of 2500 से 2000 centimeter inverse corresponds to C triple bond and C triple bond and triple bond stretching. The region from 2000 to 1500 centimeter inverse deals with C double bond, C double bond, O, C double bond and double bond stretching. Interpreting the infrared spectra. The following points should prove very useful in the interpretation of infrared spectra. Always start with the high frequency end of spectrum. The absorption band due to most of stretching vibration appear in the region above 1500 centimeter. The region below 1500 centimeter is used for the confirmation of identity. The negative evidence is more reliable. Overtones and coupling peaks. Overtones. These are high frequency bands which may occur at or near integral multiples 2 times, 3 times more fundamental frequency. The overtone at double of the frequency is called first overtone. The which appear 3 times is known second overtone. Coupling peaks. These are additional bands which results from the combination of two fundamental vibration peaks by the addition of subtraction. Fermi resonance. Usually the overtones and combination bands are much less intense than the fundamental bands, but if the energy of fundamental vibration is quite close to that of an overtone or combination band, energy is transformed from fundamental vibration to the additional vibration, thus it increase the intensity of overtone or combination band. This mechanical coupling between fundamental and additional band is known as Fermi resonance. Higher spectra of some simple molecules. Application of infrared spectroscopy. The infrared spectroscopy is highly used. Following application: identification of substance. Infrared spectroscopy is very often used to establish whether a given sample of an organic compound is identical with or not. The second, determination of functional group molecular structure. Infrared spectroscopy is very helpful in determining the molecular structure of a known substance from an examination of the position of the absorption band in the spectra. Studying the progress of reaction. Progress of a chemical reaction can be readily followed by examining spectra of portions of reaction mixture withdrawn from time to time. Detection of impurities. It is possible to determine the sample is pure or impure by comparing the IR spectra of the given compound and the actual pure compound. We can get the impurity. Some examples. How will you distinguish between CH3, CH2, CH2, NH2 and CH3 whole twice and on the basis of infrared spectrum? Answer: CH3, CH2, CH2, NH2 shows characteristics NH stretching band at 3400 centimeter inverse and NH bending at 1600 centimeter inverse. These bands are absent in the IR spectrum of CH3 whole thrice N. That is all about the chapter IR spectroscopy, which is known as infrared spectroscopy. Thank you for listening.